So, yeah, thanks a lot to the organizers for inviting me here to this fascinating workshop. I'll be talking about mostly Fermi getting up Fermi gas. This is actually from an actual picture where we can see every spin down atom in our attractive Fermi-Hubbard system, and they can demonstrate that these are paired up. Of course, make connections in a cartoon-like way, but that. First of all, that generally two strongly interacting metals. I mean, probably we can count more, but like broadly speaking, you can either have strong interactions and be lucky. For example, you use Feshbach resonances in cold, or you happen to be a nucleus, or you could quench the kinetic energy, and then you enhance the role of actions. And you can do this by going into optical lattices, for example, quenching the kinetic energy. You design your band by going to flat bands interested by graphene, or into Landau levels to study quantum Hall physics. So we are in the business of doing all these things. We have, for example, bulk superfluids of fermions. We have bosons and fermions under rotation, which actually realize Bose-Einstein condensates in the lowest Landau level. In fact, in the Landau gauge, like from the textbook, show these very elongated strips. That's actually the lowest Landau gauge wave function. And we can also switch to lattices and look at these fermions with single atom resolution imaging. So just to with plain bosons, weakly interacting bosons, can you already do some interesting stuff by going into a rotating? Yes, you can. In fact, you just need to remove the effect of centrifugal forces by using an isotropic. Then, in the rotating frame, you have perfect flat land. In fact, momentum space is always perfectly flat, and you have Landau levels. And we can create a state which is in the ground state, in the lowest Landau gauge wave function. And then we can solution of this Bose condensate just under the influence of the magnetic field and interatomic interaction. There's no external potential, there's no energy or kinetic energy in it. And what happens? So this would be this is the setup. This is the initial Landau gauge condensate. The only thing that happens is there are interactions acting. All this kinetic stuff is gone. And what we can then observe is actually a crystallization of this Bose-Einstein condensate into many droplets. And this instability actually is implied in work by Alan MacDonald, Steve Gervin, and Platzman. It is the story of magnetorotrons. I just wanted to flash because we have talked about flat bands and Alan models. I couldn't resist to show you this study. These were just bosons. Let's mix in some fermions. So if you do it the other way around, mix in a few big Bose condensate, what happens? And I will show you that's actually the simplest way you can get Planckian scattering. So let's think about it. At very low temperatures, you have these fermions placed by condensate into quasi-particles. We call them Bose polarons. Might be confusing, but they're fermions, but they live in a bosonic medium, just basically like electrons in a phonon gas. Just a bit more complicated dispersion for the Bose. At non-zero temperature, the fermions will scatter with accumulations. Now, the density of these atoms, according to Einstein, is given by 1 over the de Broglie wavelength cubed. Okay. The scattering cross-section, if we drive our interactions to be resonant at the Feshbach resonance, the only length scale is again the de Broglie wavelengths. The Broglie wavelengths, but scattering cross-section goes like lambda squared, and you plug it in, calculate a scattering rate, and you get maybe no surprise if they're not their scales kBt over h bar. We can actually measure that actually put these fermions we can perform spectroscopy on these fermions, bring them into a magnetic state using an RF spectroscopy. And if they were perfectly coherent, you would get a delta response. But if there's some other boson scattering them while we try to rotate them into a non-rejecting state, it gives you scattering and broadens the spectrum. So you see these broadened spectra, and from the width you can directly obtain the scattering rate, and it is linear in temperature. Linear in temperature, and the pressure is on the order of a few. In fact, to get some street credit, you can actually do some calculation of the scattering rate, which is done here, and you obtain that indeed on the resonance. The blue curve is for resonant. You get a linear in temperature scattering rate. This, by the way, you can look up what should happen in Subir's book, and also it is implied in the paper on Fermi mixtures, where you actually have a quantum critical point at zero chemical potential. It's hilarious. Quantum phase transition from the vacuum to the non-vacuum. It's actually interesting. It's, by the way, not a strange metal. It's a beautiful metal, as you also pointed out yesterday. Momentum is perfectly conserved, so the conductivity would still have a delta. Now let's switch to fermions. Two states of fermions. A balanced mixture with attractive interaction that actually gives us superfluids, and to the interactions gas again, using the Stretch-Bach-Feshman resonance to study this crossover from a Bose-Einstein condensate to a Barden-Schupper state of long-range pairs. We therefore quite over that these systems are superfluid. Very interesting is the situation by resonance, where you have only two length scales available to you. You have the interparticle spacing, you have the de Broglie wavelengths. Right. So in some sense, this is actually too many length scales for Subir, because we have a density, but it is nevertheless quite universal, almost just temperature, but it's actually also density. And of course, you know what happens at low temperatures. You even lose temperature as the scale. You have an energy of the system. This is on the order of the energy of a non-ejecting Fermi gas, just with an initially unknown factor that you have to measure from experiments. And it's actually difficult to calculate. 37% of the energy of the non-Fermi gas is the energy of this unitary gas. By the way, in this paper, Pablo he actually put a whole series of strongly coupled superconductors on the map, and the electron lithium that I showed you is coming closest to this critical line of Bose-Einstein condensation temperatures of all Fermi systems. Now, what about transport? When you have transport in these systems, it's actually sort of simplified, because the mean free path is as short as it can possibly get. It's one interparticle spacing. That means then that the average velocity, together with the mean free path, will actually conspire to give you a diffusivity is independent of density. This laser pointer is only virtually working, so I totally see it, but you don't. I just get this point. Right. So the velocity is given by being degenerated by h bar over m, and the distance between the particles. That's you have to localize these wave packets. So velocity times gives you diffusivity. That this looks like h bar over m, basically. That will be true for charge, spin, momentum, and thermal transport. We studied spin transport a while ago, and indeed saw that at low temperatures you actually get a settling of the spin diffusivity at a roughly constant value on the order of h bar over m. At high temperatures, this is not a linear curve. It goes like T over Tf to the 3/2 of the diffusive, which is simply coming from the velocity of the gas going like square root of temperature, and the mean free path going like temperature. One of the mean free path going like temperature. So now let's switch from spins to sound transport. And for sound, we were inspired by this experiment by these famous authors. It's a very fun thing to do. You have a box of fermions. In fact, at least we work with box potentials to make the theorists happier, to start with uniform densities. Then we shake the walls of that box. Then you see, well, there's a slight modulation indeed in the density. If you take the ratio of these two images or the difference of the two images, you see more clearly that indeed you decrease the wave. And that wave is in time, and that will be important to study the diffusivity. First things first, you can do this with all kinds of frequencies and measure the speed of sound. It is indeed a linear dispersion. That's not absolutely given because we work with a gas. So it's very nice to see that in gas become basically liquid for these strongly interacting situations. There is this fun fact that E equals 9/10 mc squared. Okay, I mean, we're very confused what I mean by that. We actually print T-shirts these days with correcting Einstein formula. What happened? Sees, of course, the speed of sound, not the speed of light, and it turns out in such a unitary gas, which is scale invariant, even though it might have a dedicated equivalent state, if you keep entropy fixed, well, then you can take out of this derivative of pressure with density the complicated part, which you might not know, and then the only way the pressure depends on density is the same way as a non-interacting gas depends on density, and we know that. And from that relation, we get E equals 9/10 mc squared. So you can measure the energy of the gas, and we can measure mc squared, and we will get a line with the slope 9/10. We can excite resonant and see why there are what the resonances we get. So we can just scan the frequency. You could basically sing this. So we are just slowly coming to a yeah. Okay, roughly. Okay. Just trying to get that. So you get various ascending waves in this gas, and of course you also see when you now make up a sonogram that these resonances become less and less well defined at higher and higher frequency. That's exactly what you expect for a hydrodynamic soup, where the width of the sound spectra increases like k squared. These are again these sounds shown as a function of frequency for all the various modes. And from the state of the width increases with frequency, you can obtain the sound diffusivity. You plot width versus frequency. It's a quadratic function because it's a hydrodynamic soup, and you obtain just by dividing gamma by a squared, the wave vector squared, you get a diffusivity. And it turns out it is on the order of h bar over m in this at this temperature, and wants to limit its sound diffusion. We again can make a plot as a function of temperature, and again see something very similar to the situation of spin diffusion. Sound, again, there is a settling below the critical temperature for superfluidity. There's nothing special happening at the critical temperature for superfluidity in the first sound, not with our resolution. And again, at high temperatures, you have yet again a T over to the 3/2 law. Now, what about superfluidity? There must be happening. Well, it's not in first sound, it's in second sound, as Tija and Landau told us. So you have to just write not only the equation for one gas, but actually two gases. So a normal fluid and a superfluid that gives you the two fluid hydrodynamic equations. I don't want to with the details, but you have in textbooks. And you will get actually two sound modes, right? You have two fluids, you get two sound waves, and this is famous helium. For example, at TC, you start having a second sound mode, which is a propagated mode, whereas above TC, you have a diffusive way of propagating heat. That speed is usually much lower than the first speed. So we have a gas that we can actually couple directly to temperature using a density probe, so we can shake our gas. And if we shake it right, the frequency of sound, should it write second sound, in other words, a heat wave rather than a density wave. That actually works. This was the first sound I showed before, and this very faint thing here, I claim that second sound. And of course, it is not listening out, and we are very sad. But of course, it is not meant to couple strongly to density because it's a pretty temperature wave. We actually came up with a way to directly measure in these systems, and it's using again radiofrequency spectroscopy. But all you need to know about the spectroscopy is that the spectra depend on temperature. If you have a spectrum that depends on temperature, like Planck's law, you can sit at a particular frequency and record the response of your gas. And in fact, you can do the spatial resolve. You can wiggle the gas, get a temperature wave. Nothing special happens in the density, but our thermometer shows locally where the hot stuff is and with sub-nanocaloric resolution. So as we do this, we now see, boom, there is a crazy peak in the second sound mode, and basically nothing responding at sound. So they're shown side by side. We open these graphs, in fact, in the same experiment. The first sound is the second sound side by side. That gives us the superfluid density directly extracted from the speed of the second sound. It looks like what you think it should look. It starts from 0 and then goes quickly up to unity, even at temperatures that are not cold. So it's 10% of the centimeter temperature. That's way above. That's way above the melting temperature of most materials. We can also now study the damping of second sound and see it siege back and forth cloud. So this is frames from that movie of heat propagating ballistically in our system and reflecting off the walls. And then also to pinpoint the superfluid transition by looking at the transition from a diffuse mode of temperature, just boringly diffusing from the hot side, to a propagating emitting mode. Damping of second sound does show something interesting here, the critical temperature of superfluidity, and that is actually known from helium-4 as well. The critical temperature of superfluidity, the second sound diffusivity of helium-4 also goes through the roof and nearly diverges. Just to summarize that part, wherever you look, diffusivities that are on the order of h/m in these gases, and of course the precise temperature is very interesting, and in some ways shows signatures of phase transition and from being dominated by fermion pairing, broken fermion pairs as the excitation, to being dominated by electrons being the excitation. But that gets a bit too detailed. I want to jump to the last part, which is the Fermi-Hubbard model, which I don't have to introduce to this audience. Really, this is way too hard for cold atoms to model these actual materials. With the Fermi-Hubbard model, one has a chance. One can put these guys on a letter and see what happens. That has been done many experiments, and this doesn't even do justice because I just ran out of space eventually of putting these papers on. A big part of it was pioneered also here at Rice group, directly demonstrating antiferromagnetic correlations in the Hubbard model. I will walk you now through a few recent things we on the Fermi-Hubbard. First, to orient ourselves. If we have lots of holes in our lattice, sure, it's a metal. If we have strong interactions and there are no holes anymore available, you have a metal. If you have 2 atoms per site, then you cannot top because of Pauli and you have a band insulator. Now fold this all together or apply a trapping potential, then you will see all these things in the band insulator in the center and outside the Mott insulator. And that's exactly what we see under our microscope. This region is 2 atoms per site, surrounded by a region with precisely 1 atom per site. This for strong the atomic limit. If we lower the interactions, we see fluctuations. We see double fluctuations, and then for even lower interactions, we get to strongly correlated metallic states. We can do a lot of experiments. We can ask about, are those fermions? Yes, there's a Pauli for correlations. One fermion doesn't want to be near another one. We can look at these double-on-hole fluctuations directly. We can also look at macroscopic properties like the density, compressibility, and obtain liquid state. And together with the microscopic correlations, compressibility and density fluctuations, we get temperature in a model-free way. But what a transport? Well, let's make a box again, because we like to start with uniform densities and apply a gradient to see what happens. Well, if you have a metal, the atoms can still move. they go all the way to the left. Or if you have a band where we have 2 atoms per side, in those old days, images they also move to the left. But if you have a Mott, nothing happens. Of course, they cannot move. It's an insulator. What about spin inside a Mott insulator? The spin can still move. It can still propagate. In fact, as I will show diffusively. Indeed, as we apply gradients in a Mott insulator, you get, after some while, a diffusion, spin up, go one way, spin down, go the other way. And we can watch how fast that happens, right? So we can, for example, imprint this imbalance by just waiting for this to happen, and then switch off the gradient and quickly the spin density relax. And from the time scale, we obtain directly the spin current run through the system. And these are for various interaction strengths, and make a plot of the spin diffusivity versus the interaction strength. And turns out, so at low temperatures, at small tunneling, so in the atomic limit, you expect a Heisenberg kind of propagation, which would give you a linear diffusivity as in this way versus u in of the atomic diffusivity has units of heat. We obtain a linear diffusivity in just quite a bit larger in terms of its prefactor than what they expected from the Heisenberg model. There might be effects that are not captured by Heisenberg. There might be a role of holes, etc., and possibly temperature. At fast tunneling speeds, you have the motion of 3 atoms that are able to quickly run around, and you get a charge diffusivity, which is on the order of h over m, if you allow me, m just the mass of the band, T squared over h bar. But for the spin sector here, if you want to call it h bar over m and spin, well, then that makes sense if you call this spin as a particle that runs around with a t squared over effective tunneling rate. We can also obtain the spin conductivity from knowing the spin. Well, we can obtain it directly by just applying a force and watching the current go. We can get it from the Einstein relation, knowing the spin susceptibility in both ways of extracting it. So for the second one, we need spin susceptibility, which we measured, and with bars, things agree. Curve is actually a calculation using numerically expansion. The problem is that they cannot go, it's a heroic effort, but they cannot go to times longer than a tunneling time, while we know, of course, spin exchange will be sensitive to times on of the spin exchange time. And in fact, there is you cannot say what the error bar is by this curve. In fact, it fluctuates, it bound with the cutoff. So it's challenging. I just want to flash the results from my colleague Wasim Baker in Prince. I haven't shown you anything versus temperature, but he has studied transport versus temperature, demonstrating that you get a bad metal at high temperatures exceeding the resistivity bound from this Mott-Rigel limit. I will say the resistivity at lower temperatures drops below that, so it's transitioning into a strain. I would say, but of course, more than 2 data points are needed. But it's very interesting to see behind actually capturing exactly the experiment. And it's an interesting pressure point or tension point between theory and experiment. Do you have a minute? Half a minute? Half a minute, great. Because I just want to tell you there is a beautiful mapping between the repulsive model that is in our minds and the attractive Hubbard model. In fact, it's a 1-to-1-to-1. What you learn about the attractive Hubbard model can be transferred to the repulsive model. The trick goes like you just don't do anything to your the spin downs become holes with a proper minus sign at the right places. So it's a full part of the transformation. And experimentally for us, it's actually fine. We can just study the attractive Hubbard model and see what happens. So I will tell you that we can into interesting regimes where we see charge density fluctuations and pairing in these systems. So this is actually again the BEC-BCS crossover just now on a lattice on the attractive things. So you have BEC of tightly bound pairs, subglass, popping on the lattice, large deflection, and for reaction you have the BCS regime. Above it you have a correlated soup of charge density wave correlations going on. So we can directly take pictures of this gas, and for selections you see lots of white. Those are doublons. But everyone also see like spin ups and spin downs. They're usually close to each other in this regime, which of course we can correlate and test. For weaker interaction, you see way more of the individual spin ups and spin downs. And of course, looking at that picture, I don't know whether they're up, but actually I repeat many images of the situation and just ask, what are the total spin fluctuations in these images? And the total spin fluctuations are directly giving you the spin susceptibility. So we actually see at large interactions on the order of 6T or so, we see 0 total spin fluctuations, demonstrating that we transition into a paired gas. That's not necessarily superfluid gas. We think we are like 50% too hot to be superfluid, but it's already a gas. It's preformed pairs in it, and we basically say what the pair size is in some ways, and understand how much of these individual singles we expect in a given snap. It is on the order of T squared reusable. As an indicator that there are correlations going on, we cannot directly look at super correlations, but we can look at the wave correlations, and we nice peak near where you expect the correlations to be stronger. As an indicator that interesting is about to happen, and hopefully, if we cool a little bit more, we should actually see the transition to superfluid in the attractive Hubbard model. Good. So I leave you with this maybe slide going from repulsive to attractive Hubbard model. There's a lot going on, exciting developments in the field. These transport methods are really challenge state of the art. We can go to geometries. Colleagues of mine who my triangular lattices. We have double bilayer and so on. So there's lots to be done. And last but not least, I want to thank my entire group. Yeah. Thank you for your attention. Yeah. Right. So one way to do that is to measure correlations. You just repeat. And for example, by measuring the total spin fluctuations, you know that this spin up over here, that's not just a loaner. It's actually entangled with one spin down somewhere in this system. Yeah. Right. So you may, yes. So you can prepare very controlled systems with a starting point of all spin ups in one layer, spin downs in the other layer, and measure actually if you have a bilayer layer, for example, and we see lot of singlets forming, and we can measure their correlations just with the Ramsey experiment. It's very beautiful. I didn't talk about that sort of stuff, but you can prepare very clean situations where you have basically 80% of the gas is paired singlets across layers, and you can measure the entanglement between those. Right. So mixed body entanglement is of course heralded by various things we've had here, but you can also create very like these particular systems where you make mix of like two systems with identical preparation, and you entangle them and read out after some while whether the entanglement is still. This usually works with small systems at the moment, like 4x2 or something, but it can be done, and proof of principle experiments have been done, for example, with bosons and Marcus grinders. So these things are coming online. It's of course more complicated.
What is the attractive Hubbard model? What is the temperature relative to T squared over U?
Right. So the T squared over U varies, of course, wildly, but the temperature over tunneling is on the order of 0.3. And roughly when you see, so when you have the order of 4, 5, 6 or so, then that is basically scratching at the super exchange energy scale. That's why you start seeing these pairs form. When you start seeing these pairs form, then you know, okay, so you have you are reaching into the middle of problem. You would say, I'm just showing that I'm smaller than U, but in fact, in this regime, it is already on the order of 8 over U with some factor, and you'll see that the gas is fully paired tells you you're very close to the super exchange energy scale in terms of temperature.
In the second salvo, how should I define? I think this is like, this is the local distribution in a sense, or I'm just about how that thinks about locally.
Right, absolutely. Very good to be very confused, because we also wondered how to get an absolute thermometry going here. So we actually have been able to measure not directly temperature, because we cannot thermometer, but we measure the pressure, the compressibility, and the density. And from three things, you can get an equation of state, which we did. And now you can get a thermometer on unit systems at any temperature. Well, what's your compressibility, density, pressure? Then I know what temperature is, and then I can see what my readout of my new spectroscopic method is. And that's how we calibrated it in terms of nano. Yeah.
So you mentioned on average. Actually, how we study the interaction of couples.
Yes.
Can you elaborate on that?
Yeah. So there's a mapping. There's Hubbard model Hamiltonian. Now I take the spin ups and leave them alone. The spin downs I flip into holes, and I have to, this works on a bipartite method. I have to put a minus sign to the power of what letter side I am, and then you do the thing, and magically the U goes to minus U. And imbalance in the Republic model becomes doping in the attractive model, and versa. That's it. Oh. Experimentally, all we do is we go from repulsive interaction to attractive interaction thanks to a special effect. So we have a special resonance that includes, luckily, a zero crossing, which I didn't mention. So we can go through zero and go to either side of but just move it in the lab by like gas. So it's an easy experimentally. But that part, everything else is bloody different. Yes.